Since we have clarified the concept of heat used in thermodynamics, we can introduce the term thermodynamic system, considered as a starting point in the study of heat. Roughly speaking, we will call the physical object of interest a thermodynamic system if we study thermodynamic processes related to the object, such as the transport of heat and energy and the conversion from one form of energy to another one. The birth of the concept of thermodynamic system can be dated back to the activity of Nicolas Léonard Sadi-Carnot, a French mechanical engineer who studied steam engines and tried to improve their performance. We have already seen that steam engines are able to do work when heat is applied to them. That is, a high-pressure steam is generated in such machines, which flows into a cylinder and pushes a piston transforming heat to motion. In his book published in 1824, Carnot defined a theoretical heat engine shown in the cross-sectional diagram, where the points from A to G denote a cylindrical vessel, the points C and D denote a movable piston, and the capital A and B are bodies of constant temperature. Carnot called the body of water vapor substance employee or substance mise en oeuvre, translated as working substance. The term work indicated that the steam does the mechanical work in the cylinder by moving the piston, which could be put in contact with either a heat reservoir, for example a boiler, or a cold reservoir, for example a stream of cold water. In this context, the working substance, the cylinder with the piston and the reservoirs can be considered as the components of a thermodynamic system. In 1850, Rudolf Clausius, a German physicist and mathematician, went further when he introduced the term der Werkzeugkörper or working body to describe such a system, and he included the concept of surroundings in the description. That helped in the study of the heat and energy transport between a heat engine and its environment, handled as a whole. As a result, the law of conservation of mass and energy could consistently applied in the form of balance equations for mass and energy describing the cyclic process converting heat to mechanical work. In 1878, Josiah Willard Gibbs, an American scientist, analyzed heterogeneous systems formed by a body or collections of bodies that can be solid, liquid, gas, or some combination of these states. He called these systems material system, and this concept could already be regarded as the generalization of any physical system, where the transport of mass, energy and heat was studied together with phase transitions and chemical reactions. Towards the end of the 19th century, the term thermodynamic system was already established, and nowadays we use this concept to describe and study any phenomenon related to heat and introduce the laws of thermodynamics. The basic ideas appearing in these historical remarks can help us to introduce the modern concept of thermodynamic system and describe its fundamental properties. A certain quantity of matter located in some spatial volume is considered as a thermodynamic system, where the region outside the system is called surroundings. The system and the surroundings are separated by a boundary. In thermodynamics, we study the exchange of heat, work and other forms of energy among the material objects and spatial volumes within the system, and between the system and its surroundings. We have already seen that Gibbs studied collections of bodies which were solid, liquid, gas, or some combination of these states. Such a description applying the state of matter shows that we can classify thermodynamic systems based on the macroscopic properties of regions within them. If we define the concept of phase as a homogeneous, physically distinct, and mechanically separable portion of a system, then this classification becomes simple. In this respect we deal with two types of systems, homogeneous thermodynamic systems and heterogeneous ones. A homogeneous system is a single-phase system, that is, the system is made of one phase only. In other words, a homogeneous thermodynamic system is defined as the one whose chemical composition and physical properties are the same throughout the entire system, or change continuously from one point to another. A simple example for a homogeneous system is a gas enclosed in a given volume, like these airbags in the photo. Here both the chemical composition and the phase of the substance filling the closed volume is the same the whole gas. Liquids are also considered as homogeneous systems. The photo shows a colored fluid in a flask, demonstrating that a liquid still takes the shape of the container but it does not fill every space in it. Nevertheless, we can only see one phase in the system and the chemical composition is uniform throughout its volume. A further example for homogeneous systems is a solid of a given material, like the block of copper in the photo, which has the same chemical composition in the entire body. In thermodynamics, we can study the transport of heat or other forms of energy in these relatively simple systems or in the interaction with their environment. A heterogeneous thermodynamic system consists of two or more phases. In such a system, each phase is separated from other phases by interfaces, where the chemical composition of the substance or its physical properties abruptly change. An example for a simple heterogeneous system is a two-component fluid, where the components of different density are separated from each other. In the photo, some oil is poured into a glass of water which do not form a mixture, but the oil emerges on the surface of the water. Ice floating in water is also a heterogeneous system where fluid and solid phases of the same substance coexist in separation. The last example for a heterogeneous system is a solid body or a collection of solid bodies, where the parts of the body or the members of the collections are composed of different materials. The photo showing some grains of sand demonstrates how different the physical properties of the individual parts of such a system can be. As opposed to the phase interfaces considered as simple thin layers in heterogeneous systems, the boundary between a thermodynamic system and its surroundings can have different fundamental properties, which determines the transport processes through the wall representing the boundary. We distinguish between three different types of transport through walls: the transport of mass, the transport of energy, and the transport of momentum. Based on this distinction, we compiled this table containing all the possible types of walls applied in thermodynamics. If the transport of mass is allowed through the wall, then we talk about a permeable wall, otherwise the wall is impermeable. An example for permeable walls is the double layers of the wall and the plasma membrane of a cell. The wall is fully permeable to most molecules, but the membrane of selective permeability helps to concentrate certain dissolved molecules and ions inside the cell. The study of the transformation of energy in thermal and electrochemical processes and transports occurring across this permeable wall membrane structure is an important application of thermodynamics. A typical example for impermeable walls is the wall of a gas cylinder, which prevents the gas in the cylinder from escaping. In thermodynamics, we can consider any substance, gaseous or liquid, enclosed some container, and study the exchange of heat between the substance and the environment while it remains confined within the impermeable walls of the container. If the transport of energy is allowed through the wall, normally in the form of heat transfer, the wall is called a diathermal wall. If the transport of energy is forbidden, that is, the wall is a perfect thermal insulator, then we talk about an adiabatic wall. Pressure cookers have a diathermal wall made of aluminum or stainless steel, which are excellent heat conductors. If we place a pressure cooker on the top of a stove, then it takes 5 to 30 minutes to heat up any food or water in the cooker, indicating an extensive heat transfer through the wall of the cooker. The function of a Dewar flask or a thermos bottle is the opposite. It prevents the exchange of heat through its adiabatic wall. Such a vessel keeps its content hotter or cooler than the environment, since the evacuated region in its wall provides thermal insulation between the content and the environment. If a wall can be moved, then it allows the transfer of momentum between the system and its surroundings, whereas fixed walls do not allow such a transfer. We can find both movable and fixed walls in an engine. If we consider the fuel combusted in each cylinder of the engine as a system, then the piston moving in the cylinder is the movable wall of the system and the cylinder represents its fixed wall. As illustrated by the pair of a cylinder and a piston, the boundary of a thermodynamic system can be a collection of different types of walls. If we classify thermodynamic systems based on the types of walls surrounding them, we can talk about 4 different types of systems which are shown in this table. The first type of thermodynamic system is the isolated system, which is separated by an impermeable, adiabatic and fixed wall from its surroundings. Such a wall prevents the exchange of mass, energy and momentum between the thermodynamic system and its surroundings, isolating the system completely from its environment. Since the wall of any Dewar flask has an impermeable, adiabatic and fixed wall, any substance stored in such containers can be considered as an isolated thermodynamic system. The second type of thermodynamic system is the adiabatic system, which is separated by an impermeable, adiabatic, and moving wall from its surroundings. An adiabatic system can exchange work with its surrounding by the momentum transfer through its moving wall. At the same time, the wall prevents any exchange of mass and energy. A typical example for an adiabatic system is an insulated cylinder filled with gas and closed by a piston, provided the transport of heat through the wall of the cylinder and the friction of the moving piston can be neglected. If the moving piston increases the volume of the gas, then we talk about an adiabatic expansion of the gas, where the gas cools down since it cannot absorb heat from its surroundings. The third type of thermodynamic system is the closed system, which is separated by an impermeable, diathermal, and fixed wall from its surroundings. An energy transfer in the form of heat exchange is possible between a closed system and its environment, but any transport of mass and momentum is prevented by the boundary. An obvious example for a closed system is the food or water enclosed in the pressure cooker. The metal wall of the cooker allows the transport of heat from the oven to inside the cooker without exchanging any mass or work. The last type of thermodynamic system is the open system, which has no wall and the transfer of any quantity is allowed between the system and its surrounding. One can interpret such a system as we draw only a hypothetical boundary between the system and its surroundings. If we open the valve of a gas cylinder, or remove the lid of the pressure cooker or the cap of the thermos, all the substance held in these containers become open systems, where the exchange of mass, energy and momentum is free. Since we have introduced the concept of thermodynamic system, we can define the state of such a system, also known as thermodynamic state. In the discussion of the combined gas law, we saw that the law determines the temperature and the pressure of a given amount of ideal gas enclosed in a volume. Therefore, the physical state of an ideal gas is uniquely described by its pressure, volume, and temperature, and we can measure all of them. In general, experimentally measurable macroscopic properties describing the state of a thermodynamic system, such as mass, volume, pressure, temperature, gravitational or electric field and so on, are called thermodynamic parameters or state variables. In the case of an ideal gas, the state variables uniquely describing the thermodynamic state of the gas with a given mass m or given amount of substance n consist of the pressure P, the volume V, and the temperature T of the gas. Although the mass and the amount of species of the gas are also state variables, they can be considered as fixed parameters if the gas is enclosed in a container with an impermeable wall. In such a case, the mass or the amount of species does not change in the system, and the state variables pressure, volume, and temperature are enough to describe the state of the gas. In general, if n physical quantities describing the macroscopic properties of a thermodynamic system, denoted by x1, x2, ellipsis, xn, are necessary to uniquely define the state of the system, then we call these quantities thermodynamic parameters or state variables. The thermodynamic state of a system is uniquely determined by a given set of state variables. As a result, we can represent the state of the system with a point in an n-dimensional space spanned by the set of the thermodynamic parameters. Since the state variables for a given amount of ideal gas are its temperature, pressure, and volume, we can plot a three-dimensional Cartesian coordinate system with the axes for these quantities. In this coordinate system, the point P represents a given set of the temperature T, the pressure P, and the volume V describing the thermodynamic state of a given amount of ideal gas. In the general case, we can use the n-dimensional coordinate space for the state variables x1, x2, ellipsis, xn, where the point P represents a given set of the values of the thermodynamic parameters. The variables x1, x2, ellipsis, xn are called the generalized coordinates of the thermodynamic system, and the vector with these coordinates describes the thermodynamic state of the system. If we classify the state variables of a system based on their relationship with the surroundings, we can talk about external and internal state variables. External state variables only depend on the generalized coordinates of external bodies interacting with the system which belong to the surroundings. For example, the volume V of a gas in a closed space is an external state variable, determined by the geometric configuration of its boundary in the surroundings. Similarly, any external force acting on the system, like the force F holding the piston at a fixed position or moving it, or the gravity acting on the gas in the container, is also an external state variable. Internal state variables depend on the generalized coordinates of both internal and external bodies. The pressure of a given amount of gas depends on both its temperature and volume, where the temperature is another internal state variable and the volume is determined by external parameters. Therefore, the pressure is an internal state variable determined by both internal and external coordinates. We have seen that the state of a thermodynamic system can be determined at a given instant of time by specifying a set of state variables describing the state uniquely. However, we have not examined whether this instantaneous state is temporary or permanent. That is, whether the thermodynamic state of a system is changing in time or remains the same. From this point of view, we can talk about a special situation. If a system is in a stationary thermodynamic state, then the state of the system is independent of time. In other words, the physical properties of the system do not change with time, and the generalized coordinates x1, x2, ellipsis, xn specifying the instantaneous state of a thermodynamic system are constant. The relationship between the state of a system and the transport processes between it and its surroundings is complex. Even if the transport of mass, energy, or momentum is prevented between the system and its environment, it does not follow that the system is necessarily in a stationary state. For example, any exothermic chemical reaction in an insulated thermodynamic system releasing heat and changing the chemical composition within the system modifies its state. Inversely, a thermodynamic system exchanging mass, energy, and momentum in the form of work with its environment can still be in a stationary state. That is, a mass or a heat flow between a steady-state system and its surroundings does not necessarily change its physical properties with time. If the point P represents the steady state in the n-dimensional state space, then the vector x constructed from the generalized coordinates of the system is a constant vector. As a result, the steady-state system will never leave this point during its time evolution, and the trajectory of such a system is only the point P representing its initial state in the state space. We can distinguish between different aspects of the thermodynamic state, talking about the thermal, mechanical and chemical properties of the system. If a thermodynamic system is in a steady state, then the system is also in a steady thermal state, and its temperature is constant. A steady-state system is in a steady mechanical state as well. For example, it has a constant volume, and it is also in a steady chemical state, where its chemical composition does not change, that is, the amounts of various species remain the same with time in the system. An everyday example for stationary thermodynamic state is the operation of an air conditioning system. As the photo shows, the air conditioner is installed on the wall of a building. The device has three main components: an evaporator, a condenser, and a compressor. The compressor is circulating the air between the evaporator inside the air conditioner, and the condenser is located outside the building. The air conditioner pulls warm air through air vents in the building and coils it in the evaporator filled with a gaseous refrigerant to absorb heat. The warm refrigerant is pumped outdoors to the condenser so that the heat can be released. The refrigerant leaves the evaporator in the form of a warm, low-pressure gas. In order to release the heat absorbed by the refrigerant, the gas needs to have higher temperature and pressure. The compressor reduces the volume of the gas to add pressure and increase temperature. The heat moves from the high-temperature refrigerant to the cooler outdoors, where it can be released through the condenser, turning the pressurized gas into liquid vapor. Then the refrigerant travels back to the evaporator, where the process begins again. In a steady operation of the air conditioner, the indoor temperature is held constant and the air inside the building remains in a steady state. In general, the effect of any process releasing heat in a thermodynamic system can be compensated by circulating some coolant between the system and its surroundings, which keeps the system at the same temperature. The steady transport of mass and energy between the system and its environment allows one to hold the system in a stationary state. In this example, we have seen an interaction between the system and the surrounding causing the state of the thermodynamic system to be independent of time. However, external processes are not always necessary to prevent the system from changing its thermodynamic state, which is formulated in the following concept. Thermodynamic equilibrium is the condition or the state of a thermodynamic system, where the properties of the system do not change with time, and no external processes take place in maintaining the state of the system. In equilibrium, the generalized coordinates x1, x2, ellipsis, xn describing the state of the system are constant in time, as in the case of the stationary state. Since macroscopic change does not occur in the thermodynamic system and no external processes maintain this state, the net macroscopic flows of mass, energy, and momentum in the system and between the system and its surroundings cease to exist. As a result, if a thermodynamic system is in equilibrium, then it is in thermal, mechanical and chemical equilibrium at the same time, which has no tendency for spontaneous change. We have seen that one of the criteria for thermodynamic equilibrium is that the net exchange of mass, energy and momentum is zero between the system and its surroundings. In fact, such a condition can be met both in isolated and open thermodynamic systems. If we wait long enough, then any flux of mass or heat diminishes and any chemical transformation stops in an isolated system. Since the transport of mass, energy, and momentum is forbidden through the boundary, no spontaneous change takes place in the system after it reached its equilibrium, and it remains in that state. In the case of an open system, the exchange of mass, energy and momentum is free between the system and its surroundings. Normally, we can regard the surroundings as a heat bath and a reservoir of various motionless substances. After the open system has equalized its temperature, pressure, and matter content with those of the surroundings via mass and heat transport, the transport processes will stop and the physical properties remain the same in the system. Therefore, the open system can also reach equilibrium and remain in balance with its surroundings. These two cases can be demonstrated with a Dewar flask or thermos. If we fill the flask with any substance at a given temperature and close it, then its impermeable, adiabatic fixed wall will prevent any transport between the substance in the flask and the environment. As a result, the substance is in equilibrium and remains in its state until we remove the cap of the flask. Then the substance can exchange heat with its surrounding and mix with it, depending whether it is a gas or fluid. After equalizing its temperature with that of the surrounding, the substance will reach its equilibrium in the open flask. When we discuss the ideal gas law, we consider the functional relationship between the state variables of the gas given by the law as the equation of state for ideal gas. We saw that the state variables of the gas are its mass or amount of substance, together with the pressure, the volume, and the temperature of the gas. The ideal gas law formulates a unique relationship between the state variables of n mole ideal gas confined in the volume V at the pressure P and the temperature T, which states that the product of the pressure P and the volume V is equal to the amount n of the substance, times the gas constant R, times the absolute temperature T. In many cases thermodynamic processes are studied for a given amount of ideal gas, where the amount n of substance or the mass of the ideal gas is constant. Then we have three state variables in the ideal gas law while the amount of substance is held fixed, and the equation of state for ideal gas establishes a unique functional relationship between these state variables, that is the pressure, volume, and temperature measured in thermodynamic equilibrium. The function f depending on the state variables pressure P, volume V, and temperature T for a given amount of substance is equal to 0, where f is given by P times V, minus n times R times T. We have already shown the plot of this functional relationship in the pressure, volume, and temperature diagram, when we derived and studied the ideal gas law. This functional relationship is represented by a surface in this three-dimensional space, where the function f is equal to 0. The equation of state confines the possible states of an ideal gas on the surface in the state space spanned by the thermodynamic parameters pressure, volume and temperature. That is, the thermodynamic state of an ideal gas is always represented by a point on this surface. In any thermodynamic process, the initial and final states of an ideal gas are always on this surface, provided both of them are thermodynamic equilibrium. The intersection curves of the planes of constant temperature in this surface are represented by the red curves for the temperatures T1, T2, and T3. Similarly, the blue lines represent the intersections of the planes of constant volume for V1, V2, and V3, and the surface, whereas the green lines represent the intersections of the planes of constant pressure for P1, P2, and P3 in the surface. This figure demonstrates that by fixing two of the state variables, we can determine the third one from the intersection of the planes of constant for the fixed state variables and the surface of the function f. That is, from the equation of state we can determine the pressure of an ideal gas enclosed in a given volume at a given temperature. For example, if the volume and the temperature of the gas are equal to V3 and T3 respectively, then the intersection of the curves V3 and T3 on the surface gives the gas pressure, which is equal to P3. Similarly, if the pressure and the temperature of an ideal gas are given, then the equation of state tells us the volume in which it is confined, and by fixing the pressure of an ideal gas enclosed in a given volume, we can also determine the gas temperature from the equation of state. Based on these considerations on the ideal gas, we can define the equation of state for general case. The equation of state is a fundamental characteristic of substances and describes the state of matter of a substance under a given set of physical conditions. The equation of state is used to characterize gases, fluids, fluid mixtures and solids, and it reflects atomic structure, chemical bonding and stability of a material. The equation of state of a thermodynamic system is a functional relation between the state variables x1, x2, xn in thermodynamic equilibrium, written as some function f depending on these variables which is equal to 0. In fact, equations of state are derived by applying thermodynamic relations between the state variables, together with either experimental measurements or theoretical calculations based on the methods of statistical physics, using various models of interactions between particles in a system. If the equation of state of a thermodynamic system is given, then it can be represented by an n-1 dimensional hypersurface in the n-dimensional state space. This hypersurface can be considered as a constraint surface for the thermodynamic states of the system, that is, its any possible state lies on this hypersurface. As already mentioned, the constraint surface describes only thermodynamic equilibrium. If the initial and the final states of a thermodynamic system are equilibrium states, then the points representing these states are on the hypersurface. However, the changing states of a system in a thermodynamic process are not necessarily confined on the hypersurface. Such non-equilibrium situations are studied in non-equilibrium thermodynamics, and the equation of states for such scenarios are derived by applying non-equilibrium methods in statistical mechanics.